Hi everyone, this is Ms. Helms, and this video is to help you complete your notes for the second part of special right triangles, and these are for our 30, 60, 90 triangles. So you don't have to watch this unless you need help filling in these notes. So, starting off, what is an altitude? This was first semester, so hopefully we still remember that information. An altitude, remember, that is the height of a triangle. So, we also referred to it as the perpendicular from any vertex to the opposite side. So it's either the height of a triangle or it is the perpendicular line from a vertex or from a vertex to the opposite side. Opposite side of a triangle. So, the altitude to one side of an equilateral triangle, since it's equilateral, is also the perpendicular bisector. So, not only is it perpendicular to the third side, it cuts that other side in half. So, is also a perpendicular bisector. So, taking a look at this example, by drawing in this altitude, FG, we have created two right triangles. And more specifically, we know that since this is an equilateral triangle, all of the angles are congruent. They're all 60 degrees. So this is 60 degrees, this is 60 degrees. Well, if this is the altitude, not only is it a perpendicular bisector, it's also an angle bisector of that vertex, of the angle formed by that vertex. So, we know that each of these angles are also congruent. Well, let's think about it. If the full angle of the measure of angle F is 60, and that FG is an angle bisector, it cuts it in half, so half of 60 would be 30 degrees. So each of these are 30 degrees. And since it's perpendicular, I'm going to draw that mark, the 90-degree mark. So not only two right triangles, but more specifically into two 30, 60, 90 right triangles, which is our second special right triangle. So we're going to go ahead and try to think about the special relationships between the sides. So as we said, this is a perpendicular bisector, so that means that DG is congruent to EG. And we're going to start by making the side length of our equilateral triangle 2. And you'll understand why in just a moment. So, if the side lengths are 2, DG and EG would have to be congruent, and since the bisector cuts it in half, so each of these are 1. So, on the next page, if we just focus on 1/2 of this triangle, and again, we said that angle D was 60 degrees, angle G is 90 degrees, and angle F is 30 degrees. We said that DF was 2 and DG was 1. And this was just back in the notes that we just did. So we want to solve for FG. We want to know what that is. Well, we can, since we have a right triangle, we can use the Pythagorean theorem. So, setting up the Pythagorean theorem, we know, and I'm going to call FG, I'm going to call this X. Okay? So we know that 1 squared plus X squared equals 2 squared. Okay, so 1 plus X squared equals 4. To get X squared by itself, subtract 1 from both sides. So X squared equals 3. To get X by itself, we take the square root of both sides. So therefore, X equals the square root of 3. So the pattern here that we're noticing is if our short leg, or DG, is 1, then DF, or the hypotenuse, is double that measurement, and the longer leg would be radical 3, or the short leg times radical 3. So again, the ratio from shortest to longest is 1 radical 3 2. And we're going to see, well, how does this actually work with these problems? So let's take a look at the first example. We're given that DF is 4. Okay, so if DF is 4 and we want to find the remaining sides, we're going to take a look at what else we know. Well, in this example, we know that this, from the hypotenuse and the shorter leg, is a 2-to-1 ratio. So if DF is 4, well, then DG is half of 4, so that's 2. So to solve for the missing side, we can set up the Pythagorean theorem. And again, I'm going to call this x. So we have 2 squared plus x squared equals 4 squared. Okay, so 4 plus x squared equals 16. So subtract 4 from both sides to get x squared by itself. X squared equals 12. Take the square root of both sides. So if we keep this in simplified radical form, the square root of 12, we think about the factors of 12. So factors of 12 are 4 times 3. We know 4 is a perfect square, so the square root of 4 is 2. And left under the radical we have 3. So x is really 2 radical 3. Okay, well, let's take a look at another example to really get this idea of the pattern. And again, remember, if we take a look, we have the short leg is 1, the hypotenuse is double the short leg 2, and the longer side is our short leg 1 times radical 3. So in the first example, our short leg was 2, our hypotenuse is double the short leg, which is 4, and our longer leg is the shorter leg times radical 3, so 2 radical 3. Okay, so taking a look at this last example. Now we're given that DG is 4. Well, now we're given the shorter leg. So to find DF, we take our shorter leg 4, multiply it by 2. So 4 times 2 is 8. So that means DF is 8. And we want to solve for FG. So again, we can use Pythagorean theorem. So we know that 4 squared plus x squared equals 8 squared. So 16 plus x squared equals 64. Subtract 16 from both sides. So we get x squared is equal to 48. And then we take the square root of both sides. And leaving it in simplified form, we get x is equal to the square root of 48. Factors of 48 would be 16 times 3. Well, we know that 16 is a perfect square, so the square root of 16 is 4, and left under the radical is 3. So that means FG is 4 radical 3. So again, paying attention, taking note, our shorter leg is 4, so our hypotenuse is double that shorter leg, or 8, and our longer leg is that short leg, 4 times radical 3. So 4 radical 3. So, last but not least, we're going to generalize this pattern. So, taking a look, we're going to say that DF is now 2x. Well, if DF is 2x, that means DG is half of that measurement. Well, half of 2x is just x. So, to solve for FG, we're going to set up the Pythagorean theorem. And I'm just going to use FG in general. I'm going to use it FG as the side length. So, we're going to set this up. X squared plus FG squared equals quantity 2x squared. So, x squared plus FG squared equals 4x squared. Remember, 2x times 2x, it's not just 2x squared. Remember to multiply those coefficients. So to get FG by itself, we're going to subtract x squared by itself, x squared from both sides. So FG squared equals 3x squared. And to get FG by itself, take the square root. So FG is equal to the square root of 3x squared. Well, the square root of 3 is not a whole number. It's not a perfect square, so we're going to leave that under the radical. But the square root of x squared is just x. So FG is equal to x radical 3. Or this is our shortcut. This is telling us, well, what is the shortcut for this one? How does this work? And again, this is only for 30, 60, 90 triangles. So if I go ahead and fill in our angle measures, we know that this is our 60-degree angle, this is our 30-degree angle, and this is our 90-degree angle. So the shortcut is the shorter leg is half the leg of the hypotenuse, and the longer leg is the shorter leg times radical 3. So, for example, if I said the shorter leg was 8, the hypotenuse is 2 times that short leg, so that would be 16, and the longer leg would be whatever that shorter leg is, so 8 times radical 3. As we said before with the special right triangles for 45, 45, 90, you do not have to memorize this pattern. What you really just need to remember is this 2-to-1 ratio here between the hypotenuse and the shorter leg. Knowing that, you will be fine for all of these problems. So, to summarize on your last page, based on your conjecture, in a 30, 60, 90 right triangle, if the shorter leg has a length x, then the longer leg has a length x radical 3, and the hypotenuse has a length of 2x. The ratio of short leg to long leg to hypotenuse is x radical 3, 2x. Nice work.